All right, welcome. This is electricity. I'm going to be doing some of these videos maybe a bit out of order. Hopefully I won't be referring to things or repeating things too often. The advantage is that you can always fast forward video, find other spaces. It won't take too long, so get through it. But just wanted to say welcome to our new unit, probably going to be our last unit. Unfortunately, we might not get a chance to get to space, so we'll have to see where things end up. But the electricity is a very important unit, and so we've got to make sure we get through this, and then the space, which is very interesting, is more fun, so we can end on a high note. This is the first lesson, so you notice that this is section 10.1, so we are skipping ahead. So our chemistry chapters 4, 5, and 6 of the textbook, we shifted backwards for ecology for chapters 1, 2, and 3. Now we're going to go ahead to chapters 10, 11, and 12 to the end of the textbook, and then space is the last one in between chem and electricity here. What you are going to do for these is key terms will not be as important for this unit. Biology, or as you might have noticed, is a bit more memorizing, so that's why I wanted you to get all the key terms written down, because knowing those definitions is very important. With electricity, we do have definitions we have to learn. Some of them we will be familiar with, hopefully, from chemistry already, so we have a little bit of groundwork in, but there's a lot more practical to this. So the textbook will be helpful for this purpose, and this works out well distance learning because we were already done chemistry. We started off biology with sort of minimal textbook work because it took us a while to get it, but now some people have mentioned some issues with access to the textbook, but those problems I think have been fixed, and no one else has said anything, so I'm assuming here that the textbook is working for everybody. So with that being said, the homework at the first slide for each of these sections for these chapters, because remember, usually you've been noticing the pattern that each chapter has about 3 lessons, 3 PowerPoints in them. You can do the homework that will be on the first page of those. I've modified it from what we would have been doing in class, so this will be part of the lesson tutorials. I was noticing that the ecology lessons weren't super long. I was managing to get those down. The earlier ones were a bit longer, so there wasn't. So that's what. Anyways, so these lessons I'll try and make, except for this one because it's the intro. But the other ones will be shorter, hopefully. So you will be able to do a combo of watch these videos, or even just read the textbook, whatever works for you on your own, and then just doing some of these questions for practice, because that will be very important for this unit, is getting a kind of concept introduced to you and doing some practice with it, getting some hands-on work. That will be the best for this unit. So you notice that the biology was a lot of just kind of studying, memorizing notes, and those types of skills, whereas this unit will be maybe similar to the chemistry in that you'll need the practical to help you with it, and that's what these homework questions will be for it. So the section is outlined here. You can see which one, you can see what work there is to do for that. Because you don't have an electricity package. Right, I just realized that now. Okay, well that's good. We'll work through it. So anyways, the lesson, the info will be here. There's no notes to fill in per se, so you can watch these, read through the text, and then do these questions. So that'll be good. That'll help you with those. I don't know if I have an electronic copy of blanks to fill in, unfortunately. Why don't we get to it then? Going through these slides. So what is the electricity? It's a very broad topic. Let's just get some definitions of what we're referring to. So it's a form of energy. That's the key word there, is that electricity is basically just energy that results from the interaction of charged particles such as electrons and protons. Hopefully you remember these words from the chemistry unit. If you don't, go back and read up on them, because I'm assuming that you know what they are, and your understanding of what they are as basically these little tiny particles with negative and positive charge on them and they are subatomic particles because they make up atoms. That understanding is pretty much all you need. You don't need a deeper understanding than that, but the key thing is that they are very small and they have negative and positive charge. Protons are heavier than electrons as well. Electrons move faster than protons will also be. So all that's review. We obviously need electricity, which I'm sure we are all experiencing now with having to be online all the time. But electricity has a cost, right? It's not free, monetarily free, or resource free. So we were talking about the environment with our ecology unit, and we can talk about how our energy demands impact the environment in this unit. So hopefully you're seeing a connection between all of these units, that there is a little bit of overlap between all of them. Hopefully makes learning things a bit easier if there's connections. So looking for alternative electricity sources is obviously something I'm sure that you've heard of and that humans are trying to do, because our current methods are unsustainable. And there's the word conservation. We have to conserve electricity as well to lower the amount that we need, right? So not only finding different sources of energy, but also moderating the ways that we use energy. Okay, there's two types. This slide is very important. We have static and we have current electricity. Static electricity, you probably have heard of, but the sort of textbook science definition, an electric charge that tends to stay on the surface of an object rather than flowing away quickly. So static comes from the word which means not moving, right? That term static on its own does not necessarily only apply to electricity, it can apply to other situations. If you have someone sitting in a chair that hasn't been moving for a long time, they are static, they are not moving. So static electricity is the form of electricity where electric charge has been built up and the charge can't move. We contrast that with current electricity. That is an electric charge that flows quickly through a conductor in a closed pathway. We're going to talk about this word conductor in a bit more detail, but for now, all we need to know is that current electricity refers to charge that flows, charge that moves, just like current, like a current of water or the current in a body of water. If you go swimming in the ocean or a river, people say, watch out for the current, because that's flow, right? It's the water flowing, and it can pull people out, so to be careful. So two different types that we're going to look at. Chapter 10 is going to focus on static. Current electricity is going to come a little bit later, but we will start getting an understanding of each of these. But notice the common thing between them. We mentioned that electricity is a form of energy, but we also said that, oh, hey, there's charges, protons and electrons, and we see that charge shows up in both definitions. So we have to sort of talk about that a bit more. So like we said, static means not moving. Static charge is the charge that tends to stay on the surface, okay, like we said. And that the term surface is also going to be important here, that the charge of whatever the object is going to be close to the surface. It's not going to get into the bulk of the material, and that not super important for this level, but maybe just a good thing to include in the definition. Okay, how do we create static charge? Well, there's three ways. You can charge by what's called friction, induction, and then contact. Okay, there's a little fun. That's just a fun slide. You get your neutrons are free of charge, because remember that neutrons don't have charge. So a little joke there. We'll talk about ways to generate it, but let's go back to our model of the atom for a second. So this slide right here should be reviewed. Looking at this slide right now, you should say, oh yeah, I remember this. If you don't, go back and review it to get to the point where you can understand what we're talking about here. So remember that the Bohr-Rutherford model, remember that these were two different people, right? Niels Bohr and Ernest Rutherford, two different scientists. We combined their atomic theories into this one model because their theories are very similar, so we sort of put the ideas together. And in that Bohr-Rutherford diagram, in the Bohr-Rutherford model, as it were, right, this is the diagram down here, we have protons with these little pluses, right, so these purple ones, and neutrons, which are these yellow ones, which have no charge, are in the middle or in the nucleus of the atom. Electrons, with these little minuses that are gray, are in little orbits, are in little orbits around the outside of the nucleus. So The protons and neutrons live inside the nucleus. Protons are positive. Remember that the P for proton, right, and P for positive, and then N for neutron, which is also N for neutral, right? If you can remember those, then electron is the sort of the odd man out, but there's only one other charge, which is negative. Maybe a way to help you remember. Protons, neutrons in the middle, electrons on the outside. Very important there. So why are we talking about that? Well, we know that these subatomic particles carry these charges, right? The charges can't be created or destroyed. That's really important, right? We might have mentioned that when we talked about matter in chemistry. I can't really remember, but these charges can't just be like, they don't just disappear, right? They always have to go somewhere. And sometimes if you have it, you can have a buildup of charge. And you have to sort of deal with, and then you have to deal with the charge. So static electricity means that charges can't move, and then charge can build up. And since these charges can't just be destroyed, they have to go somewhere in order to flow or to move around. Okay. What we call this term a net charge on solid objects results from the transfer of electrons between this object and another object. So remember what we're talking about. Electrons are how chemical reactions happen. We said that electrons can be transferred between atoms, right? Now, on the chemistry unit, we said, okay, this is how maybe like a sodium atom gives up its electron to fluorine, which happens for a chemical reaction. What we're talking about with electricity is larger materials. So we're no longer, we're sort of in between. We are on an atomic scale because we're talking about electrons, but we're no longer talking about electrons necessarily doing chemical reactions. We are talking about a transfer of electrons between different materials, right? Like when you're combing your hair and then you get like an electric shock, or when you touch a doorknob and get an electric shock. Those are instances of electrons being transferred, right? There's no chemical reaction per se happening there, but electrons are transferring from one object, maybe like a comb, from your hair to the comb that you're using, or the hairbrush or whatever, right? Electrons going from one to the other. Since we have so many electrons in these materials, because we're talking about millions and billions of atoms, millions and billions of electrons, there's so many that in exchange of just a couple, we don't really notice from like a chemical perspective, but we can sense them in the form of maybe an electric shock. Sorry, all that to say is that electrons are the only thing that get exchanged. Protons, which are also charged, do not move. They stay exactly where they are. So that's going to be an important concept to get. It's going to be, I think, tough at the beginning because we have such a wide range of things to discuss and to talk about, and so these early lessons will be a bit more confusing because we have so much to cover. So just kind of stay with me as we go through and maybe write down questions on the side and email me if you have them, but wait till we're done. Maybe wait till you're done a whole lesson and then sort of let it sink in and sink in. Okay, so let's take a look. If the object has more electrons than protons, right? Remember that electrons are negative, protons are positive. The object will be negative overall, right? The net charge will be negative. This term net may be also from finance. If you talk about net income, those of you that have jobs, or if you know anything about jobs, what's your net income, right? You look at money going in, right? That you get paid. Let's say you work at Tim Hortons. The money that comes in from your employer, but you have to pay for a couple things, right? There's taxes on that. Maybe there's employment insurance. Maybe there are union dues, right? So there are some things that come out of your paycheck automatically. So what you see when you get that paycheck isn't the full amount because there's some things that are reduced, right? We refer to that as net pay. So basically, Tim Hortons can say, okay, we're going to pay you, $10 an hour, right? Well, of that $10 an hour that they promise you, there's some things that are going to come out. So it might not be an exact 10, maybe it's like 8 per hour, right? We refer to that as the net. Just important to point out, just for financial reasons. It does seem a bit strange, right? But everyone has to pay taxes. And then a lot of these fees that come out are very necessary. But sorry, I'm not talking about finance. Just want to point out what that word net means. So basically, it's sort of like an input versus an output is the overall, right? It's similar to this. Protons are positive, electrons are negative, right? It's almost like sort of like an input, versus like an output, right? Money that I have versus money that I owe. If that helps, maybe kind of get this idea of deficit or surplus, right? It's very similar when we talk about these charges. So here we go. More electrons, negative. But if it has less electrons than protons, then we have a positive object, right? Different materials will hold onto their electrons with different strengths as well. So we have two conditions. Basically objects, right? Large objects, not large, but just objects in general can have one of two charges. Well, it can have three, right? They can be neutral, have no charge. They can be negative, they can be positive. Neutral, well, how about this? What situation will neutral arise in, right? If we have negative with more electrons, we have positive with less, what situation would neutral have? Why don't you think about it and pause the video now. Okay, good. You hopefully said that the neutral situation, right, for something to be neutral, will have to have an equal number of electrons and protons. So we see three cases. Either we have more electrons, we have less electrons, or we have an equal number of these two. Okay, so our atomic structure, remember we have a neutron with no charge, the proton which is positive, and we have the electrons around the outside, right? Which have this negative charge. We see that we have two protons in the middle, and we have two electrons on the outside, which means that net, overall, we have no charge, because this pair, they cancel each other out charge-wise, and then this pair cancels each other out charge-wise. The neutron contributes nothing, so it has no charge. So overall, no charge, zero, nothing, right? But what happens in the situation where we gain an electron, like we talked about in in the chemistry unit, right? When we transfer an electron there. Well, all of a sudden, we have, okay, this pair still exists, this pair still exists, right? Because these guys cancel each other out, because a positive and a negative, what do they make? They make nothing, right? If I owe someone $1 and I have $1, then I give the person $1, I don't owe them any money anymore, right? It works out perfectly. But what happens if I owe someone more, like $3 and I only have 2, right? Well, I still owe them 1. Does that make sense, right? Anyways, we see that this positive and negative pairs, if we can lump positive and negative into a pair, right, 1 to 1, then we say that they cancel out and they are neutral. There's no overall charge coming from them, right? Just looking at this overall, because however you want to imagine, like the whole charge of the atom. But throwing in an extra electron leads us to the situation where we have a negative charge, because look, there's no proton to balance this negative. Another way, I'm just going to overload you with analogies. Hopefully one of them will stick. If this is like a slice of bread with peanut butter, and this is a slice of bread with jam, right? We need 1 jam and 1 peanut butter to make a full sandwich, right? So we have a whole sandwich. We don't have any excess slices of bread sitting around. Same thing with this situation here. But we accidentally put peanut butter on another slice of bread. We don't have another slice because we don't have another slice with jam on it, so we can't make this sandwich, right? So we see that this is incomplete, meaning that it's excess, right? It's extra. And by how much? By 1. By 1 unit of charge. And this can only arise from gaining or losing electrons. The number of protons is fixed. It will always stay the same. It cannot change. So the overall charge on an atom, we get the overall charge of an atom when we compare the number of protons to the number of electrons. This should hopefully be some review, but we have to go into more detail, so it's very important that you understand. So, find videos on YouTube, read the textbook, whatever it helps. Send me an email, ask me questions, but this is the really important thing to understand. If you have trouble with this, please let me know, because you will have trouble with probably this whole unit, right? Okay, negative charge if we gain an extra electron. However, in this other situation, what if we take away 2 electrons? So we see that we added 1, right, to get the negative charge. What happens if we take 2 away, right? So the one that we added and one of the original ones. What's going to be left overall? Well, again, we see that we have 1 positive-negative pair here, but we have no partner for this proton because we removed it. So however you want to think about it, you know, peanut butter and jelly. We have one sandwich, but we now have one jelly bread, right? We don't have the peanut butter to match it with. So hence overall positive charge. Okay, what is the cause? So, like we said, it's the number of protons and neutrons, right, in their atoms, fundamentally. When we think about this, remember that there are billions of these atoms, right? So the situation we talked about here is one individual atom, but there's billions of these, right? So you think about each atom having like a pot, you know, there's a whole bunch of atoms that can have different charges on them at any one time, and so we're looking at the aggregate overall when we talk about like objects, because I'm talking about like things that you can like touch, right? Like a glass, a comb, a wall, a balloon, your hair. All of those things are objects, right? Composed of matter, made of atoms. But we can see, we get shocks. I touch that doorknob, I get a shock, and that's a result of a charge imbalance. Of all of the billions of electrons that are in both objects, there's an imbalance in them, a slight different number of electrons in one object than there is in the other, and that's what causes shocks, and that's what causes static electricity. Hopefully that makes sense. So static charge builds up as materials are rubbed together. So this is one way that we can create charge. It's called charging by friction, right? Friction is just the force that's produced when two objects rub up against one another. And they can exchange electrons when they do that. And then that's called charging by friction. When electrons from one material will get transferred to the other one, right? What's going to happen? If I transfer electrons from one object to the other one, and if the electrons can't really move around, they're going to stay on the surface of each of the new object, and the original object is going to be positive, the object where electrons have moved to will be negative, and then now we have a charge on both of these objects, okay? That's called friction. So when you rub things together, physically touching and rubbing together is how we can charge. We can actually cause electrons to move, right? And so the actual textbook definition is the process which objects made from different materials rub against each other, producing a net static charge. This is also very important, the fact that they are different materials. Rubbing the same material together can have no net transfer of electrons, because if it's the same material, it has the exact same hold on electrons. We're going to talk about what's called the electrostatic series with a bunch of different materials that have different strengths of how they hold on to these electrons. Just like we talked about with our atoms, how some atoms, like the alkali metals, if you remember, they give away electrons, or metals tend to lose electrons, whereas non-metals tend to gain them, right? So larger materials are very similar. Some prefer to lose electrons, some prefer to gain. Like we said here, because some have stronger hold, right? So basically, you can think about that electrons are being pulled off the material with the weaker hold, and they're transferred to the material that has the stronger one, right? We have to be careful when we start using this term attraction, because we're using this word to refer to charged objects. So be careful when we use this word attraction, but basically you can picture it like electrons being pulled from one material to the other one, right? They both get charged due to the excess or deficit. Remember that deficit just means like not a lot of, or a shortage of electrons, okay? So materials with strong attraction, right, or strong holds, right? Let's keep this. A strong attraction to electrons become negatively charged, right? So this is a material that wants electrons will become negative. Materials that don't want electrons will become positive, right? It makes sense because electrons are negative. Here's an example from the textbook. We can see that we have a comb and we have this girl's hair. We have negative and positive charges. That's what these little black lines mean. One line like this is a negative charge, and then the little plus is a positive. And these are just individual charges, right? If you look at the comb and the hair, there's an equal number of positive and negative, right? They balance each other out. So what are the charges on each of these? Neutral, right? Each of these things are neutral before we're touching, right? I know it looks like it's touching, but it's not. This is before combing, right? But then after we comb the hair, we notice that, well, hey, there's some of these negative guys are missing. Some of these negative charges have actually moved to the comb, right? Because we can see some extra ones on the comb. So after we've combed the hair, these negative charges have moved from one material, hair, to the other material, the plastic in the comb. Hence, the comb has a negative charge, the hair is going to have a positive one. Now, why does this happen? All we need to know about this is it just depends on the material. And I will let you know which materials have stronger holds when compared to other materials, right? We can make a list of these different materials. So the comb basically has a greater ability to attract electrons. The comb just has a stronger pull on electrons than the hair does, however, right, for whatever reason. So when they are touched and rubbed, the comb pulls the electrons out of the hair, and that's how we get the resultant net charges, right? Again, electrons are the only things that move, protons are not moving. So the positive charges, notice they haven't moved, only these negative ones can. We can arrange these materials in a series because they're all relative to each other, right? So we can call it what's called an electrostatic series. Electro just because we're talking about electrons or electricity, static because it's static electricity, and then a series because it's a list, right? It's several different things. Okay, closer to the top, they have weaker hold on electrons, which means that they lose electrons and they're going to become positive if they are rubbed with something near the bottom of the list. Substances on the bottom of the list have stronger holds, they become negative, right? So let's take a look. Here's an example of the series, and this is the one that we're going to be using, right? This is the only one that we're going to have to use. Really, really important. Do not memorize this. You will not need to memorize this. Anything that we do with this, you will always be able to look this up. Not a bad idea to get this into a place where it's easy to access. If you want to, I'll put the PowerPoint up. You can download this picture, right? And you can take it out of the PowerPoint and put it somewhere electronically so that it's easy, print it out, whatever you want to do. But a lot of the homework questions are going to be relying on this series here, so it's going to be important to get. Again, do not memorize this. You do not need to memorize this thing. Okay, materials at the top, like glass or human hair, right? They're at the top of the list. Their strength of electrons is weak, right? So glass and human hair do not have a strong hold on electrons. They have a weak hold on electrons. So these guys are probably going to form positive. They will have a positive charge if rubbed with something below them on the list. So let's look at the things on the bottom. Ebonite is what this is. It's just a black form of rubber, right? And it's not soft. It's very rigid. So this is called ebonite, and then like a grocery bag or whatever, right? So this is polyethylene, just plastic, right? A different type of plastic than is in the ebonite, right? There's lots of different types of plastic because they're made up of different atoms. Ebonite and grocery bags are on the bottom. They have a strong hold on electrons, which means they form negatively charged objects. So what the series is going to look at is if we say, okay, we have like a wool object that is being rubbed with silk, right? Like a wool sweater is being rubbed with a silk scarf, whatever. If those two things are rubbed together, right, the way the situation is going to look at, we're going to take two things, we're going to rub them together, and then we have to compare where they are on the series, and if whatever's higher will transfer electrons to the thing that is lower, right? So we have to first describe how the electrons get transferred, and then we say, well, what's the resultant charge? And we have to identify what the charge will be on each item after rubbing them together, right? So those are the types of questions that we're going to see dealing with electrostatic series. Now, insulators and conductors. We're going to shift gears a bit, so that we're sort of halfway through, or at some point through, but we have to give some new definitions now. So we're all the stuff we just talked about, let that sink in. If it's overwhelming, pause the video now, come back to it at this point later, because we're going to, obviously similar stuff, but we're not talking about some of the stuff. It's a little, we're changing topics a little. So pause if you need to. Okay. Materials listed in the series, right, are nonmetals, and then they're going to be considered what are called insulators. This term, insulator, sort of like insulating, right? Now, what is an insulator? An insulator is a material in which electrons cannot move easily from one atom to the other. An example of insulators are like wood, rubber, and plastic, right? Notice that all three of these things are non-metal. So in general, non-metals will tend to be insulators, right? Electrons don't move very freely in them. Remember that this is just a measure that there's different levels of insulators. And we're talking about like a a spectrum of how easy it is to move. Let's finish this slide and then I have an analogy for you. Metals, on the other hand, are considered to be what are called conductors, because they are materials in which electrons can move easily between atoms, right? Copper, silver, aluminum, any type of metal. So two different class of compounds, conductor or insulator, right? Now these are somewhere on a spectrum, as well as our friends semiconductors, which are the metalloids, right? So it says non-metal, but remember our metalloids, the staircase on the periodic table, those guys are going to tend to be semiconductors, right? Basically, they're in between these two things. They're not quite insulators, they're not quite conductors, they're sort of in between, right? Semiconductor is very important for computing, right? That's why in California it's called Silicon Valley, right? That's why, because you need silicon is a component of computer chips, right? And semiconductors are also important for making computer chips, like processors and things like that, like so that your computer can basically, so it can work, sort of like the brain of the computer. And it's composed of silicon, right? An element, and that's why it's called Silicon Valley. Because in California, in San Francisco, there's a place where lots of technology companies go based off of computing, right? So places like your Facebook is in Silicon, I don't know, Menlo Park. I don't really know my geography that well, but like Apple, Silicon Valley, IBM, Microsoft, all those big companies come from this area, and that's why, because you use silicon in these things. The analogy I was going to give you, picture like how easy it is to run on certain surfaces, if that makes sense. A conductor would be like a nice flat, like asphalt road, very, very smooth and easy to run on. If you are just like running or walking, it's very easy to walk or run on a sidewalk, right? Now, so that's like a conductor. Like in this case, electrons are the things that are walking, and then the material is like the ground. Now, is it easier or more difficult to run, let's say, on grass, right? Well, maybe short grass, not a big deal, but maybe you're not going to be as fast, or maybe you'll be, who knows. What about longer grass that hasn't been cut in a little while, right? It's going to be a little bit harder to walk on that. Compare that also with what about mud, walking through mud. That's very difficult. It slows you down, right? So we have all these different situations where we can run on things, and this is very similar to insulators and conductors, right? They're just talking about degrees of movement. So an insulator some insulators can still have a very small amount of electrons moving through them. It's not like the electrons are completely not moving. It's degrees, right? So I just want to point that out, because some insulators can conduct a little bit of charge. It's just it's just sort of like how much, right? And there's a threshold. And if you want more info on that, that's actually not this level. So if you want to know more about it, then please go ahead and read up on it. But we don't have to talk about it too much at this level. Okay, let's talk about grounding something and how we remove static charge. To get rid of all of this excess charge is to connect the material to what's called the ground, right? And you're like, well, like the ground I'm standing on? Yeah, that's it, right? That's what that term means, right? When we say the ground, like that's what it is, right? So whatever you're standing on. Basically like the earth, right, is what you want to connect that to. So what is ground? An object that can supply a very large number of electrons to, or can remove a very large number of electrons from a charged object to neutralize it. So that's what the ground basically is. It doesn't have to be ground per se, but that's what it is. So whenever you touch something to the ground, it's connected to the earth, right? And the earth has like so many electrons that it can supply or it can take without really changing its net charge, if that makes sense. So the earth is going to be neutral all the time, no matter what happens, right? And that's sort of and so when you get that electric shock, it's because you had charge that was static in you, but whatever you were touching was connected to a ground of some kind, right? That's how people get electrocuted. If you're in contact with something that conducts electricity, but you're not connected to the ground, the electricity doesn't flow through you, right? As soon as you touch a ground, though, then you've created a pathway for electricity to flow, and you can get electrocuted. So so that's a safety precaution. And so by physically touching these objects, right? And sorry, rather you yourself can ground some objects with low amounts of charge, right? So when you touch something, then you might even be acting as a ground per se. So there's different sort of definitions for it. And this is the symbol here, right? Sorry, this is not that. The symbol down here, right? These three lines kind of going vertically, that references the ground. Okay, great. Stay with me because I'm actually going to show you a few things. I'm going to switch up the pattern because I may as well make the most out of the screencast because we're talking about lots of stuff, but visualization is going to be helpful. There's this great website. If you just Google this, PHET, and then simulations, or even just PHET, you'll get this page that will come up. And they have, it's based off of, I think, University of Colorado. But if you go to the physics section, which is the second link, I'll show you. If you go to the physics section, you'll see a bunch of simulations that are all maybe Java or Flash. And they're little applications that you can play around with, right? So I have clicked on this balloons and static electricity to give you an example. Now this one's kind of fun to play with, but it's good for me demonstrating, but there's lots of things that you will be able to. So, Google this and play around with it by all means, because it will definitely help. We can see that we have our sweater with our positive and negative charge, and we have our balloon, right, with, again, positive, negative, and then we have our wall with a whole bunch, right? So we have different numbers of these. What you can do, if I click on the balloon, notice that all of these things are neutral, right? I guess this is going to be a bit later, and we'll talk about attraction, but see how that they're all neutral? What's going to happen if I rub my balloon to the sweater? Okay, if I rub the balloon, look what's happened, right? Don't worry about the charge per se, but if you take a look at the balloon, look at all these negative charges on it, right? All those blue circles are now in the balloon. I've taken them from the sweater and I've transferred them to the balloon. And then obviously there's an attraction there. We'll talk about that in another lesson, so we'll come back to it. But I want you to think about, well, which one of these two things do you think would be higher on the electrostatic series, right? Remember the electrostatic series. Which of those two things do you think would be higher, the balloon or the sweater? Okay, pause the video. Okay, you have your answer. Which one? The sweater is higher on the electrostatic series. Right? It has a weaker hold on electrons so since the balloon took the electrons, it means that the balloon has a stronger hold. If the balloon has a stronger hold, the sweater has to have a weaker hold. Therefore, sweater is higher, balloon will be lower. And we can see the resultant charges that we see all of these positives, right? What do you think the net charge of the sweater is? Positive. What is the net charge of the balloon? Negative, right? And then we see that we have the wall, which we'll kind of factor in a little bit later. So I just wanted to show you that transfer of these. Now, both of these objects, sweater and balloon, are probably insulators because we notice that the charge does not flow away. The charge stays on the surface of the object, leading to a net charge of it, right? So these are probably insulators. Okay, I think that's about all I wanted to show you. If there was another video of friction, I sort of showed you the transfer, and I hopefully showed you the net positives and how all that matches up. But there are lots of great videos on there, as well as good things in the textbook to help you visualize and understand what some of these are. Okay, try the questions and that learning check, and I'll see you soon for the next lesson.